Hello class, it's time for part 1 of our lecture on measuring pressure. So first we'll start with a little review on what pressure is, starting with pressure on the molecular level. Some of these concepts here are going to be important to explain a few devices we're going to cover. So first, we'll start with all molecules above absolute zero have some kinetic energy. Kinetic energy means they have velocity. Velocity means there will be collisions, and specifically collisions on the boundary volume. So those collisions result in a force per unit area on the boundary volume, and that's what pressure is. It's a force per unit area. So here we have that basic equation for what pressure is. It's force over an area, and we have this little image up here that shows that. So force over area, pretty simple. Units, we have our English system, which is pounds per inch squared, often abbreviated as PSI, pounds per square inch. I added this little note here that the pounds is pounds force. Make sure you remember pounds force, not pounds mass. In the SI system, it's newtons per meter squared. The unit that is all of that, the newtons per meter squared, is a Pascal. So PA abbreviation. Now we're going to look at what factors affect gas pressure. We have two of them here. We're going to give a third one in a minute. But first we have velocity, which is a function of temperature. We already talked about that. And then we need to incorporate in mass. So it would be the mass of those molecules. As an example, argon versus hydrogen. So argon, you can see, much more mass than hydrogen. Those two combine to give us momentum, which is obviously important in the force per unit area that we're after measuring. Then the third one is going to be the density, and that's going to dictate the frequency of those collisions, which is also important. Now we're going to talk about some useful gas laws you should be familiar with. The first one is the ideal gas law. Here we have that equation. Einstein wrote it on the board. PV equals nRT. P is the gas pressure, V is the gas volume, N is the amount of gas in moles, R is the ideal or universal gas constant. R is equal to the Boltzmann constant times Avogadro's constant. And like it says, it's the universal gas constant. There's some students get this confused with each gas could have its own constant. There's a subscript with that R. This R is just that universal one. It applies to all gases. The equation is slightly different when you have the R. I think it's the M instead of the N. But this is the one we're focusing on. So remember, this R is the universal gas constant. It's the same for all gases. And then T, the absolute temperature of the gas. So temperature in Kelvin. The ideal gas law is a good approximation of behavior of many gases under many conditions. Other gas laws are special cases of the ideal gas law where one or more variables are held constant. And we're going to use one of those a number of times in this course. So Boyle's law, here we keep the nRT constant. So PV, pressure and volume, are going to equal a constant. So this is mostly useful in looking at essentially two different states of a system. So here we're seeing that the temperature is staying the same. The temperature, so we said the temperature is staying the same, and then the amount of material is staying the same as well. So that's constant. We're just changing the volume and the pressure. We're seeing that as the pressure goes up, the volume goes down. As the volume goes up, the pressure goes down, which is illustrated here. Should make sense. Next, we need to learn the different types of pressure we'll come across when measuring. It's measured in three forms. First one is gauge. So this is the state of a substance relative to the ambient pressure. A lot of times when people are talking about pressure, just in common language, they're talking about the gauge pressure. So this figure down here, we have a perfect vacuum. Then our pressure increases. This scale is kind of arbitrary, but we're showing some real high pressure up here. So ambient, this isn't necessarily to scale, but gauge is going to be, so ambient is just that. It's the ambient pressure. It's the atmospheric pressure, 1 atmosphere. So from that to whatever pressure we're trying to determine, that would be our gauge pressure. And then absolute pressure is going to be gauge plus the ambient. So it's our pressure relative to a perfect vacuum. That's this one. The third one is differential. We don't really show that one down here in our figure. Specifically, you could say, we could use the gauge one as an example. It's a pressure between 2 points in a system. Gauge is more specific though. Say we just had some point here. It was like we're measuring flow and we needed to measure pressure at different points. We'd measure a differential pressure. We'll get to that where we learn how to measure flow by measuring pressure at 2 different points. So why measure pressure? I just gave one reason right there. We're going to look at a bunch of others though. So these are just some common things you might come across. You'd want to measure tire pressure. Most modern vehicles automate this. You might see your tire pressure in PSI show up on your dashboard. You might just have a little light that shows up when your tires are getting too low. There's actually a number of different mechanisms of how that pressure is measured. The most common ones are just kind of integrated into the stem. There's this little module behind there, and that speaks to the computers in your car wirelessly. There's some other methods that measure how fast your wheels are spinning. There's usually like where a metal passes, or you have like the metal tooth on a gear type of thing that passes by a magnet wrapped in a wire. And when that metal passes through that magnetic field, a pulse is generated. So the rate that the tire is spinning, that that RPM is measured through that device. And then if a tire is, so they'll have one of those on each of the wheels. And if a wheel is spinning faster than one of the others, it means it's lost pressure and it's gotten smaller. So it'll spin, it'll need to spin faster to keep up with the others. That minute change is something the computer can detect and say, hey, that tire's likely got too low of pressure. That type of system is a lot less common than the ones where there's, say, just like this little module here that has a piezo element in it. Normally in class, I have one from my vehicle some tires. I bought some extra wheels for my snow tires, and those I think they work fine. It just didn't get the computer talking to them. So I always have those lights on when I'm driving my car around in the winter with my snow tires on. But it gives me a good prop to demo for you in class. But we're doing this online, so can't show you that today. Let's move on to the next one. So here we have just measuring blood pressure. There's a lot of different medical conditions that can be diagnosed by measuring pressure in the body. So that's very useful. If you like to fly planes, or you like to be in planes where the pilots can fly them accurately, which is usually a good thing, the pressure would want to be measured to determine your altitude, also to determine how much air, how much oxygen you have in the cabin. It's good in weather forecasting. Similar to the plane, a scuba diver wants to know how deep they are, and they want to know how much breathable air supply they have left. Anything related to sound, I shouldn't say anything related to sound, but sound is most commonly pressure fluctuations. So if you want to measure the noise produced by a motorcycle, the sound of a Harley is a designed thing. Just thinking of that because there's a motorcycle here, but transducers like this head and torso simulator, there's a couple of diaphragm condenser microphones in the ears of these, and this guy's setting up a microphone too. All those are measuring pressure. Acoustics is heavily into pressure measurements. So I mentioned if you want to measure the flow of some fluid in a pipe, measuring the pressure at 2 different points. So it looks like it's tap here, tap here. A differential pressure is measured here. We're going to talk a lot more about that, but know that is one of the main applications for a mechanical engineer. So being able to control hydraulics, you need to know the pressure. Same for lots of different functions mechanical engineer or a MET might come across. Welding, for example. Pressure is hugely important if you become a mechanical building systems engineer. So the pressure that a fan is going to see and how efficient that fan works, just as an example. I'll bring this up again later when we talk about inches of water as a unit. Very common unit in American HVAC design. So we're coming to the first of the devices we're going to look at. We're going to look at a lot of different pressure measuring devices. This is the first one, Utube Manometer. So the premise is that it measures the weight of fluid displaced by either a gas or a liquid. So we have, it's a tube, it's U-shaped, so that's where it gets its name. The premise is we have one pressure here, we have another pressure here. So this could be differential, could be gauge if we had this one of them as ambient, or if we had one of them like evacuated, if we sucked everything out of here, create a vacuum, we could measure absolute. But so for this one, just think more differential. We'll get to that vacuum one. You'll see that in a slide coming up here soon. But the main point here is that this pressure is greater than this one, and it pushes this fluid towards this side. And we're going to get a difference in the height of the fluid columns on each side. And that difference, that change in height, which is sometimes denoted as R, that is the basis of how we determine the pressure. So that and the density of this fluid. This first equation will have a little bit more to it, but we're going to condense it down to what I just said for a lot of cases we're interested in a minute here. But let's start with the bigger picture. So it measures the weight of a fluid displaced by either a gas or a liquid. So we could have a gas or a liquid over here. We'll talk about what the requirements are. So this obviously is a liquid. If this is a gas, aren't a whole lot of special requirements. If it's a liquid, there are some special requirements. We'll get to those in a minute. But first, this formula, the change in pressure, so the differential pressure between these two, is equal to the change in height times gravity, because we need the weight, of this fluid here minus the sensed fluid here. So that's how we get the change in pressure. That equation there is particularly important if we're measuring a liquid. We're going to simplify it down for gas here in a minute. That note that popped up is just saying sometimes change in H is R. You might see either of those symbols for this one. So on to that thing about simplifying it for gas pressure measurements. If we're measuring gas, the manometer fluid is much more dense than the sensed fluid. So we can just drop the sensed fluid density out of the equation. So this is more, if you're measuring a gas, this is the equation you're going to be using. I should put a red box on this one. The change in pressure equals the change in height times gravity times the density of this fluid. Then you can get the change in pressure for a gas. So like I said, a liquid can be measured, but there are certain conditions. First, the manometer fluid needs to be more dense than the sensed fluid. It needs to be immiscible, so they're not going to mix, right? We need to have this boundary here. So oil and water would be an example of two liquids that could be used. And they need to be different colors too. You need to be able to see where one ends and the other begins. Now, moving on to a variation of that one, the well-type manometer. This one has a little bit of an improvement. If we were in class, I would be asking you why you think that is before we get to this point. Maybe you can pause this and think about that for a minute. But seeing that I already have number 2 up here, you can probably, if you're reading these, you can already understand what the main advantage is. So just because of the configuration of this, because we have this much larger area over here, the H1 remains constant or nearly constant. So we're not getting nearly the change in height over here as we do in the capillary on this side. So because of that, only H2 needs to be read. And that minimizes readability error. So we reduce the error some using a well-type manometer. Now here is the one where I was mentioning there's a variant of it where you could have that P2 as evacuated volume or a vacuum. So here, that's what we have. So this is a mercury barometer. It's meant for measuring the ambient temperature, so relative to a perfect vacuum, or however perfect this vacuum can be made practically. So again, this one's well-typed like the last one. It's just measuring relative to a vacuum. Now, a few general notes about Utube manometers. First, we have the range. So we can use different manometer fluids. If we use mercury, that's the Hg. So we have 13.6 grams per cubic centimeter. And we had a 10-foot capillary. So this is a 10-foot tall manometer. If we had that filled with mercury, we could measure up to 4 atmospheres. So this would be approximately the upper limit of what is practical to measure with a manometer. If we were more going for sensitivity, we'd want to have a lighter fluid in there. So for light oil, where it's 0.5 to 0.085 grams per cc, then the minimum pressure changes we can measure would be, with this Utube manometer, roughly 1/2 inch of water. I'm going to get to that unit here soon. It comes directly from this unit with the fluid column height. So I guess we could just, we're at that point here in the notes. So this H2O unit, first we should mention it's equal to 1.23 times 10 to the -3rd atmospheres. But the unit comes from the height of the fluid column, like I said. So if you had water in here and you had the pressure difference that displaced it 1 inch, that would be 1 inch of water. It's common in expressing atmospheric absolute pressures. And like I said, when we're looking at the applications, it's common in mechanical building systems design, or HVAC. So as you know, density is temperature dependent, so temperature will affect this. Therefore, it's common to specify inches of water at 4 degrees Celsius. The reason 4 degrees Celsius is chosen is because at that temperature, water is exactly 1,000 kilograms per meter cubed. So our U.S. customary units, foot-pound system, imperial, however you want to call it, this is that density. So at 4 degrees Celsius, we would want to use this if we're using the inch-pound system. These would be good things to keep in your notes, because it's not only useful for this unit, but it's also common to specify the density of a fluid relative to this. So when we do that, we'll specify the specific gravity, which we symbolize with capital S. That's the ratio of the fluid density to the density of water. And again, typically at 4 degrees Celsius. So if something was twice as dense as water, if it was 2,000 kilograms per meter cubed, you would have a specific gravity of 2. S would equal 2. We're going to get to an example here pretty soon that looks at these. First, let's look at how sensitivity can be improved in a manometer. This would be another thing that I would quiz you on if we were in class. But again, we're not. So I'll just go forward with it. The way that you do it is with an incline manometer, as is shown here. So here we have the change in H and the R. In this device, those two things are different things. In just the plain old Utube manometer, they were the same thing. But here, they're different things. So change in H is the change in height in the Y direction. R is the change along the length of that inclined manometer leg. Slanting the tube results in a greater displacement of fluid. So in the other one, where we would have gotten this change in height, we get a small change. It would, instead of this, we'd end up getting something more like, what is this? This looks like it's a little more than twice as much as this. So we get more output, right? We're getting more displacement per the input, the pressure change. So we get a higher sensitivity. The equation in this one, for this one, this is another one that should have a red box around it. The change in pressure equals R. So this is what you're reading. It's easier to read more accurately because you get more displacement, times gravity times the density of the manometer times the sine of theta, the degree that it's angled up from the horizontal. So this r sine theta is just going to be, that's what's going to give us the height here. And that will be, so if we multiply that times gravity and the density like we did before, we get the change in pressure. So this reduces the minimum pressure change that we can realistically measure with a manometer down to 0.1 inch. Remember, we were saying it's closer to ½ an inch of water with the Utube manometer. Now, a summary of the pros and cons of manometers. Pros are they're accurate and simple. Cons are they have a limited range of pressures that can be measured. So like we showed, it has to be less than 4 atmospheres. That's what we would be able to, or that's what would be limited to if we had mercury in a 10-foot manometer. It is temperature dependent. So we have to keep track of temperature and the density that goes with that. It's not suited for dynamic measurements. We can't hook it up to our DAC and look at our data in our pajamas while we're home under coronavirus quarantine. This device, you have to go there and look at it and measure it. Then, as we said, the regular Utube manometer has a minimum resolution of roughly a half an inch H2O. And if we incline it, it's more 20% of that, or 0.1 inch H2O. Now here is that example. It's the first example. So there's not really much of a problem statement on this one. We're just given a change in pressure of 150,000 pascals. And we are told the density of our manometer fluid is 2,000 kilograms per meter cubed. This, if we converted it, would be 2 grams per cubic centimeter. If, say, we ended up having a test problem on this, you might be given the 2 grams per cubic centimeter and have to convert over to the kilograms per meter cubed, because that would work better with the units in like the pascals that you're given in this equation that we're eventually getting to. And that would incorporate another step into making this a worthwhile problem. We will need gravity. It might have been better to just say, at this point, find the change in H. So then you would have to say, okay, we're going to take this formula. The one you got in the slides, it had the change in pressure was equal to the change in height times the density and the gravity. So you would rearrange that like this to get the change in height. So that's going to be equal to the change in pressure, which we have up here, the density, which we have here, and then the gravity, which is a constant. It was written down up here, maybe a little preemptively. But one other consideration before we got to this point would have been it's a gas. So our manometer fluid is going to be much greater in density than that of the gas we're measuring. Therefore, we would have had this formula. I guess I should have done that before we got to this. But in any case, we're down here now. We've gone through everything up above. Now we just need to plug things in. Pretty easy in the SI system. So 150,000 pascals, or 150 kilopascals, or 150,000 newtons per meter squared. Actually, some of these units I wrote down here. So Pascal, Newton per meter squared. A Newton is a kilogram times meter per second squared, which you should know. So a Pascal is a kilogram times meter over meter squared times second squared. You could simplify that down a little bit if it helped, which it looks like it does down here. But let's plug in the rest. We have the 2,000 kilograms per meter cubed and gravity. So down here, we took the 150,000 divided by the 2,000. So that's where we get the 75. And then we have the Pascal units right here. And down here, we have the 9.81, and we have these units combined. So kilograms, this cancels out one of these, meter squared, second squared. So most of this is going to cancel out except for 1 meter down here, which will pop up into the numerator. So this equals 7.65 meters, which is roughly 25 feet. That's a tall manometer. It's almost or roughly 2 stories in a commercial building. It's tall. A solution, this would be another thing. If we were in class, I would ask you, what can we do to make this better? So think about that for a minute. The answer's already here, so you probably already saw that and can tell me the answer right now. I don't need to think about it. But if we did instead use a more dense fluid like mercury, so that it's almost 7 times the density of whatever we were using up here. So if we put that in down here instead, we don't have to mess with all the units. We know all the units work out if we put in kilograms per meter cubed down here. We would get 1.13 meters, or 3.69 feet, which is much more manageable. One more example. This one, we start with a change in pressure equal to 58 psi. So this is in the inch-pound system, foot-pound system. The question is, what is this pressure expressed as inches of mercury? And here we have a specific gravity for that mercury equal to 13.6. So we're not really told up here that it's a gas, but in the problem solution here, we're saying it is, right? The manometer fluid is much more dense than that of the gas. So we can use this equation. So this one is basically doing what we did before, except for we're incorporating in the specific gravity of mercury, and we are doing a problem in the imperial system. And that, so this part, pretty straightforward. Remember, we talked about this just being the ratio of the fluid density to the density of water, and we told you to have these in your note sheet for the final. We're going to use, so our 13.6 that we're told is the specific gravity of mercury is going to be equal to the fluid density of our mercury over that of water, which would be 62.43 pounds mass per foot cubed in this case, because it's imperial units. So we have that here. So here's that density. Here we're moving that density of the water from the underside of that ratio, from the denominator of that ratio, over to the specific gravity. So these two multiplied times each other equals our manometer fluid. And gravity in this system of units is 32.2, or more specifically 32.17 feet per second squared. And then up here for the pressure, we have to put in the 58 pounds. So PSI, we make it pounds force per inch squared. So the units here are probably the trickiest part of this. So this part isn't too tricky, but we do need to convert the inches to feet because we have feet down here. So 12 inches is 1 foot. So 12 squared would be 144. 144 inches squared per foot squared. So this is going to convert our inches to feet. But here we have pound. So this is really the key. We have pound mass down here and we have pound foot up here. So you need to put this conversion factor in here. And I know this seems kind of convoluted to many of us, especially the foreign students in this class. I can only imagine. This is all for we want to have the convenience of saying a pound mass is equal to a pound force. X pound mass is X pounds force on planet Earth. But it does create some problems when we do a problem like this. So to get these two to cancel out, you need to put in this conversion factor. Essentially, it cancels out that gravity down there. But if you do this, all the units work out. You get 9.8 feet of mercury, or 118 inches of mercury. If this doesn't make sense, if you're not trusting me on this, go and find one of the calculators. You should be able to convert 58 psi to inches of mercury. And you should get something like that. So that's it for those examples. We're going to move on to some other devices. The Bourdon tube is the first one. So I think I've mentioned this in class before. The way this works, you apply a pressure, and we have this tube. If the pressure in this tube increases, then this is going to move. If it increases greater than the ambient, it's going to move out. And through this mechanical linkage, that's going to move this needle on this scale over here. So essentially, we're converting pressure to displacement so we can measure what the pressure is. And that concept of converting pressure to displacement is going to be quite common in all these. So it was what we were doing in those Utube manometers. We were displacing the fluid column. Here we're displacing the needle. All these other cases we're going to be displacing other things, or we're going to be measuring that displacement with different devices. That's a common theme. Specifically about this Bourdon tube, let's look at some of the limitations. First, cheap ones have low accuracy, so roughly 5% of full scale. Expensive ones can be good, so reduce that by a factor of 10, roughly 0.5% of full scale. There are lots of moving parts in here, so it requires a lot of maintenance and it fatigues with many cycles. Now, we come to the question of how could we improve this device? So everything we discuss here is just analog device. Again, it's moving a needle. You need to be there and physically see it and read it off that scale to know what the pressure is. It's not the most convenient thing considering all the options we have with all the cool equipment we have today. So how can we take this old analog device and make it into a dynamic digital device? One way would be to attach a strain gauge on here. So we just learned about strain gauges. That's what this is. If our last lab number 10, this is what you would be doing. And that lab has a lot of technical skills in cleaning off this Bourdon tube and not only like getting off all the gunk, but using rubbing alcohol to remove the oils from fingertips, stuff like that. And then we adhere, so using super glue, a strain gauge, that's this, down onto the tube. There's an interesting technique for that we'll demo in the video This one has had the little, so whenever the group finishes this one, they just tore off their leads. The strain gauge just hung there, or was still adhered there, but the little leads that would be trailing off from here were ripped off. But when you get this thing, it would have about 1.5 inches long, possibly maybe a little less, 1 to 1.5 inch long lead off of each side of here, off of each of these little pads. And you would solder wires that you would then run into a Wheatstone bridge that you would then measure output voltage using a DAC VI that we would set up. And then we would send a bunch of different pressures from a compressor. So you'd enter into your VI what pressure, actual pressure we were measuring, and at that point you'd get a reading, a voltage reading out of that Wheatstone bridge corresponding to that pressure, and you can then, by measuring a number of points along there, you can do a linear regression, find a line of best fit, which would be your sensitivity, and voila, you have a digital dynamic Bourdon tube. You can read and collect data digitally through LabVIEW or similar program. We'll still demo that. We'll still give you the data so that you can determine that sensitivity, and you can apply it and look at error. But unfortunately, you'll have to miss out on a lot of the handheld technical experience that is associated with this lab. You can always get a soldering iron, and you can order these strain gauges a few dollars each. You can get a Bourdon tube from Home Depot for a couple dollars. Maybe you have a compressor laying around, or you can borrow one from somebody. So you can try this out yourself. I guess the DAC part might be a little bit difficult, but you could always just get some fixed resistors and use a multimeter. Might have that laying around. It's not too expensive. If you're really motivated, you could find a way to do this yourself. Anyways, let's talk about a few other implementations like that, where we're using a device to convert pressure to displacement, and then we're measuring that displacement. We just covered displacement, so you're going to see a lot of those devices showing up here as well. We just mentioned, so some of the devices that are going to displace from the pressure are shown here. We just talked about the Bourdon tube, bellows, diaphragm, corrugated diaphragm, and a capsule. I'm going to spend more time on those on the next slide, so let's just get to them. So the first one, the bellows or potentiometer sensor. So here you have two different pressures inside and outside of this. You say pressure 2 is greater, then this is going to displace in this direction. So we should talk about probably in the other way. This would be the side that's moving. So this moves, and we have that displacement connected to a potentiometer. So it's the variable voltage divider. We get a voltage output that is relative to this resistance over this resistance, which tells us how much our slider has displaced from this change in pressure. So we make that into a dynamic device. So here we have a capsule. So we have a reference pressure, we have a pressure signal. If this pressure is greater, then this is going to displace this way. And in this case, we have it connected to an LVDT. So remember, we studied LVDTs, we did a lab on them. You should know how this works. So we're getting dynamic displacement measurements that would correlate with the pressure. The passive sensors, so here we have these essentially two chambers. So pressure on one side, pressure on the other side. Say if pressure 2 increases, then this diaphragm here is going to move in this direction. So that's going to reduce the distance between the two plates. So these are the two plates of a capacitor. So you should remember we said capacitive sensors as well. So you should know then we get a change in capacitance that we can correlate with the change in pressure. This one can be really sensitive. You can measure really small pressure changes with this. So this is what's commonly used for measurement in acoustics of sound pressure. Also, high-end studio microphones or maybe even live performance microphones as well. They're called condensers. Capacitors used to be called condensers. That's why condenser microphones are called condenser microphones. It's because they have a capacitor in them. So we learned something about that, but another reason why I want to put this up here is just to show how sensitive these are. All of these have been damaged, and these can be damaged really easily. I had one of these in a padded case, and I didn't even drop it. So it was a thick padded case. It wasn't even dropped. It was kind of like a suitcase rolling through the airport, that type of a suitcase. And I didn't drop it, like I said, it just tipped over. It was sitting on its base on wheels, and somehow it got tipped over. And just that sideways motion, even in padding, it broke it. And that was probably $1,100 just gone like that. These are expensive and delicate, but they're highly sensitive. So here we have a diaphragm with a strain gauge sensor. So this is kind of similar to that capacitive one where we have this diaphragm and we have a pressure on each side. That diaphragm deflects with the changes in pressure, but instead of changing capacitance between that and a fixed conductive plate, we have a strain gauge embedded into the diaphragm. So put that strain gauge in a Wheatstone bridge, apply source voltage, get a voltage out that you can relate to the change in pressure. Here we have a piezoelectric sensor. So this one it's a little bit different than the others. This one, it has direct contact with measurand. Hopefully you remember, we said piezos quite a bit. So a pressure on that area is going to result in a force, and that is going to result in a voltage output. So we see a couple images of it here. Because that direct contact says no loading and quickly responds to transients. There's no like bellows or diaphragm that has to move or anything like that. And these are useful up to pretty high frequency, 30 kilohertz. I think this is where we're going to stop for this point. Last semester, this is where we stopped. So in a normal lecture, this would be about as much as we would cover. We'll pick it up with pressure part 2 for Thursday. See you then.